Hello, hi. I'm Jag Raman. Thank you all for being here. So I would like to give you a quick update on the status of DRTM using the TrenchBoot project. Sorry. And then I would also like to give the. So today we'll go over what DRTM is briefly, its current status, and how we decided to implement it. DRTM, or Dynamic Root of Trust Measurement, is a form of measured boot. It is an evolution of Static Core Root of Trust Measurement, or SRTM, where the trust resides in hardware, but it starts at the power on event. There are a few disadvantages to this approach, which is that the TCB for SRTM is large. It starts measuring various software components right from the power on, including the firmware, grub, and other software modules which don't play a role in the execution of apps in the OS. It also makes re-establishment of trust in TCB a little complicated, as we will revisit later in the presentation. In order to address these drawbacks, the Trusted Computing Group introduced a new model called the Dynamic Root of Trust Measurement, where the trust still resides in hardware, but it does not necessarily start at the power on event. It can start any time that we choose based on our implementation at what is called as a DL event, or a dynamic launch event. We will go over the advantages soon, but this is a diagram from the TCG specification that gives a timeline of DRTM. There are three distinct phases. So there is a gap phase where we don't understand the trustworthiness of the TCB. We are not sure if the TCB is compromised or not. And there's a pre-gap phase where we know that the TCB has not been established because it's coming out of power on, or we believe that the TCB has been compromised. And there is a post-gap phase where we believe that the TCB is trusted. This gives a block diagram of various components involved in our implementation of DRTM. It begins with the SKInit AMD instruction, and that kicks off the measurement process. It clears all the PCRs in the TPM, and then the trust propagates all the way to the OS, where we have a established TCB. The current status of this project is we have divided this into two sections. One is the power on phase, which executes when we come out of reset, and that we have implemented it. There is another phase called the relaunch, which my coworker Ross Phillipson is still working on, and we will provide an update when it's available. And what relaunch does is, whenever somebody believes that the TCB has been compromised for whatever reason, they can save the user state, jump back to grub, and kick off the DRTM again. And then it should be a quicker process. And when we get back to the OS, we restore the user state, and now we have a quickly established trust without losing the user state. So this one goes over the differences between Intel and AMD approach, but the most important thing is how similar they are. That's because the TrenchBoot project already had an implementation for Intel, where it used Intel's ACM, or Authenticated Code Module, which is provided and signed by Intel. So for AMD's approach, what we did was we replaced ACM with SKL. And SKL is something that the TrenchBoot community develops, and then we actually sign it ourselves. And a couple of other differences between Intel and AMD is that the DL event for Intel is the sEnter instruction, whereas for AMD is the SKInit instruction. Intel uses TXT, and AMD uses AMD Secure Processor, or ASP. This provides a bit more detail on how we implemented DRTM. So as you can see at the bottom, the hardware components used in the process. The first one, most significant one in this case, is the AMD ASP, which is a pre-existing piece of hardware, and they extended it to support DRTM by implementing a user app called the DRTM UApp. DRTM UApp has a state machine that drives the TPM, and we can control that using a mailbox register from the CPU. The TCG spec requires the presence of some hardware for DRTM that can cryptographically measure the software modules and extend these measurements to TPM. And the spec also requires that we block access to the RAM from I/O devices when we perform the DRTM sequence. So when we start off the DRTM sequence, the grub is the one who initiates this phase. So what grub does is checks if the system supports SKInit instruction, and if it does, it blocks a large section of RAM from I/O devices, so we can't, so somebody cannot modify what we are measuring. And what it also does is disables, or it parks all the auxiliary or application processors, and only lets the bootstrap processor running for the measurement process. So once grub sets up the pre-gap environment, it kicks off the SKInit instruction with the address of SKL binary as the operand. The SKInit instruction first verifies the signature of the SKL binary. Once the signature is verified, it measures the SKL and then extends the measurement into the TPM. It also sets the TPM, or it unlocks the locality 2 of TPM, where we are able to write to various PCRs, which is not possible in other localities. So now that the hardware has confirmed that SKL signature matches, it's what we expect, and then SKL does the same, and it boots into what is called as the measured launch environment, which is essentially a Linux kernel, which without an init ramfs. Instead, it has uroot, which is our own Go-based file system, which we adopted from open source. What uroot does is it checks the PCRs, reads the TPM for the PCR values, and compares the value against what we expect it to be. If there is a match, then it will go ahead and unlock the secrets necessary to jump into the target OS. And the MLE also brings the auxiliary CPUs out of the parked state, so now all the other CPUs come back alive, and it also enables access to the RAM from the I/O devices. So this part quickly goes over the individual sections. We already saw this in the previous diagrams, but just to quickly mention, the role of the grub is to set up the pre-gap environment and to kick off the DRTM sequence. So grub sets up the ICRs, it puts the auxiliary processors in a parked state, and then we start the DRTM sequence. Secure kernel loader is a binary that so the diagram here describes the layout of the binary as defined by AMD. So we have to conform to this layout. And then it measures and extends the MLE kernel. And then so currently we sign the SKL binary ourselves. And MLE is the kernel that has uroot, which confirms the PCR's match, and it also makes policy decisions whether to unlock the secrets or not. So this is our upstream status. So we have patches in review for Intel TXT support. We are still waiting for feedback. Thank you. And then so once we've got some significant feedback. So we'll be posting a V8 of the patches shortly. Thank you so much.
So you want to take questions at the end?
Before we switch.
Yeah, or are there any questions to Jack regarding that part? Do you have any questions? Before we move on? Jack,
yeah.
Simon, we have a question.
Oh, hi. Hello.
Can you measure the BIOS in Grub?
So the question is, can you measure the BIOS in Grub? So in this case, we can measure it, but we are choosing not to do it because we want to keep the TCB as tight as possible. So we are not measuring those modules in this case.
Skills. What if someone replaces one of them? You wouldn't notice.
Sorry,
yeah.
In general, Grub does not have access to the PCRs which are available for DRTM, so cannot measure. You cannot use. So you can use SRTM together with DRTM, and sometimes even suggest that it is better approach. But in general, DRTM, so Grub is not able to do measurement in the same registers in the TPM as DRTM does. So they are completely separate works.
Yeah. Hello. Hi.
I have a kind of similar question.
Yeah.
What about code running in the SMM?
So
how DRTM can, I don't know, disable, isolate, or whatever?
So we had the same question. So the question is, what about SMM, and what if somebody gets control of SMM, they can take over the system? So we had the same question for AMD, and their response to us was SMM is assumed to be trusted on AMD platforms.
Okay, so but you don't measure firmware, so how?
So
it's not exactly true story. Like, this is probably a quick answer from someone who delivers BIOS.
Okay.
But to address that is there are some mechanisms that AMD delivers, like containerization of the SMM, and there is essentially in spec stated how to do that. And of course, Secure Core PC from Microsoft that requires that, and they implement that. The Secure Core PC certified devices implement that, so it is possible. There is just no open way right now. The spec is there; someone can implement that.
Project View did some.
Yeah, Project
stuff
View
and
got some
reuses
open
this
code for that,
supervisor.
so this can be used as a reference. To also comment Simon's question, the DRTM, the point of DRTM is to re-establish root of trust. So that's on purpose technology created to neglect what was before. So just to avoid all this complex supply chain, which is bear by BIOS. So that's the purpose of the DRTM. Of course, this is not so easy, and then we can go have very complex discussion about SMM, DMA, and all that stuff. Yeah, but I guess like we can move that to after party because it's then getting very complex when we go that way. Yeah.
Okay, thank you so much.
Probably muted.
How about now? Is it okay? Okay, so let's start. So thanks, Jack, for that. So you already know a bit about the TrenchBoot project. So now we will take a look about another practical application of TrenchBoot project as Anti Evil Maid solution in QubesOS. My name is Maciej. I am currently over 7 years in FreeMDep, currently at the position of engineering manager. I am open source enthusiast, interested in embedded systems, contributing to various open source projects. As FreeMDep, we are involved in various open source communities, mainly QubesOS, Yocto, but also others such as FWPD. We are also Open Power Foundation members. We did some work on Raptor, Talus 2, Power 9 platforms. So what we will talk about today, we start with some, we had already some introduction about the TrenchBoot in general. Now we will have some introduction about the QubesOS Anti Evil Maid solution based on TrenchBoot, what is its current state, and what are the further plans. So pretty simple. Let's see. So we will not cover the whole progress. It's regularly updated on various conferences. We've given some status updates on last 2 QubesOS summits. So we'll cover the progress since the last one, which was October last year. You have links if you want to watch the previous ones, feel free to. So just a few words about what Evil Maid attack is and why we want to prevent that with TrenchBoot. So Evil Maid attack is one when you leave your device unattended. Someone has physical access to that and can tamper with that. And you, for instance, come back to your hotel room and you don't know whether your device was tampered with or not. And the Anti-Evil Maid solution aims to provide you with some tools to maybe not prevent, because that would be quite difficult to prevent such attacks, but at least give you some information whether your device was tampered with by some external person or not. In terms of QubesOS, we have QubesOS Anti Evil Maid solution, which was already there. It's a set of scripts. Right now we are improving, extending that based on TrenchBoot to support broader variety of hardware, for instance TPM 2.0. And it requires TPM, so it requires some piece of hardware, and also it requires DRTM, which was mentioned before, so some silicon vendor feature, either from Intel by AMD currently. So what's the current state? In short, we have released 2 milestones in the last month, and we are just starting another one. If you want more details, there are links to GitHub milestones. These 3 were funded by the NLNet Foundation. So yeah, links are there, and we'll now briefly cover each of them. So the milestone number 2, it was about QubesOS Anti Evil Maid solution on Intel boards with TPM 2.0, because previously we had only some support for 1.2. As you saw before, there are many parts in TrenchBoot project. In the previous presentation we saw a bit maybe different use case, because we saw the one with Linux kernel. With QubesOS we use grub and then Zen hypervisor, and not Linux directly. So for each milestone, for each phase, we have a set of GitHub actions releasing the packages, so you can download them and install in your QubesOS installation. We also have a blog post which describes how given milestone was verified, so you can also reproduce that if you are brave enough. So as the project is ongoing progress, it takes already a few years in total, we can say. There are some changes in the upstream TrenchBoot boot protocol, so the phase 3 was aiming to align with that, with the TrenchBoot Anti Evil Maid solution. So again, we have a set of packages you may use and install, and we also have a nice blog post you can read to have some more insights on that one. So we are just starting phase 4, as I said before. That one is about AMD platforms. We want to cover both TPM 1.2 and 2.0 solutions. We are still selecting hardware. Right now we think about Asus KGP DX16. It's quite old already, but it allows us to verify both TPMs. It can also have open source firmware based on QubesOS. So that is one we might use here. Another one is some Supermicro board. There are some Qubes 4.2 installation issues. We have some discussions open, so we are still considering that one. At least with the latest version, there were some problems. What are the further plans? So after we finalize the or maybe not after, we are already scoping the phase 5. Its goal is to bring UEFI support as well, because so far all of the previous one were focused on the legacy boot only. For the phase 5, we want to support both Intel and AMD platforms with both TPM 1.2, 2.0. So we are finalizing the scope to gather the what needs to be done basically, and we plan to publish that as another GitHub milestone. So if you're interested, you can also follow that topic. And definitely the UEFI one is interesting because nowadays it's the most common one for many boards. So it brings opens up a wider hardware variety in terms of what we can actually test on which boards we can use that solution. Another thing on our roadmap is further improvements of testing and documentation. As you saw, the project consists of multiple moving parts. We have Zen, we have Grab, we have Anti Evil Maid scripts. Installation, even though we have some CI, we have some packages, QubesOS packages being built, it's still a tedious task to do it manually to test recent changes. So we are aiming to automate that as much as possible. In the last status, we shown some progress in that area, but it was only on QEMU to have some automated installation of the Anti Evil Maid solution. Right now we are pursuing to move that forward, so we can also use that on real hardware units, not only on emulation targets. And also it would be nice to automatically pick up packages from GitHub Actions with latest changes to see what the result is. Another one we are interested in is upstreaming AMD Linux patches. Maybe it's not directly related to the QubesOS Anti Evil Maid solution, but to TrenchBoot it is. So Jack said about the Intel upstreaming effort, which is a very demanding task. As we see, it's version number 7 and counting. We've secured an NetNet grant for AMD equivalent of that port, so we could be able to help here. So we need to sync up on the latest changes with Oracle. Ideally, the Intel patches are merged, so we can have easier time posting another set of patches for TrenchBoot to the Linux kernel mailing list. Another areas we are interested in, as we are developing Dashara open source firmware for some of the platforms. So we have control over the firmware part, and we can make sure that all of the properties required to actually use the TrenchBoot can be properly configured. And if there are bugs, we can at least try to fix them. So that would be very nice to have TrenchBoot running with Qubes and perhaps also without Qubes on different hardware targets supported by Dashara. We already do use some of that. For instance, on the Dell Optiplex, one of the older series, we use that one for testing for the current phases. So we use a core boot firmware with CBIOS as a legacy solution to test what we currently have. But we aim to also, once the perhaps phase 5 is completed, with the UEFI support perhaps the Nova custom laptops which are already certified in QubesOS as well. And another idea, since that the testing is mostly done by us at that point, we could use maybe some help if there are some folks interested in that. We know there are, because we have already some reports, but it's not that easy to jump into that. So we're considering also to make it a bit simpler. Maybe set up. Currently, you can already download packages from GitHub Actions, from GitHub releases, but maybe we can set up a package repository with TrenchBoot packages with TrenchBoot patches, so you can more easily install them and try them out if you are interested. If that sounds interesting, you can feel free to join Matrix channel. Let us know so we can try. We can gather some attention and see what can be done here. So that was it. Any questions? Sure.
I have a question. As I saw, you are strongly insisting on still implementing support for TPM 1.2. I wanted to understand why do you want to support such hardware, and do you have any hardware which supports DRTM and TPM 1.2? Very interesting for me.
So the question is, why do we still support TPM 1.2, and do we have hardware supporting that? Yes, we started with TPM 1.2. So, for instance, the Dell stations showed here, they have TPM 1.2. These are like yes, but they can run core boot. They are really open source because they can have even memory initialization natively in core boot without FSP, correct? So there are quite
similar for ThinkPad's EX230.
Yes,
they also have 1.2.
When they were produced?
Quite a while ago, but it is the last one that you can have fully open.
Implement. Okay, run core boot and other stuff.
Yeah.
Okay.
Yeah.
yes, you can have RAM init open source and ME discarded as much as possible.
Okay.
So they are popular among those people, which are here on the FOSDEM.
I understand that on some old platforms you do not support UEFI or something like that. You just run
Well,
I understand.
yeah, okay.
Yeah. But do you?
We will, anyways. I have to test the UEFI part for TPM 1.2.
Yeah, I know.
And
Two questions. One, you mentioned you fetch in your CI packages from GitHub Actions. How